Okay, I think we can start. Thank you for those of you that attended in person. There's going to be a lot of people online anyway as well. And a lot of people might be late because it is graduation ceremonies today, I believe. Yeah, so welcome here. Most of you have seen the emails from me at Westhouse. Somehow I got the short straw to be in charge of the NITheCS North node for the time being at least. And we're trying to set up the whole NITheCS structure and the node. So we decided it's a good idea today to maybe start with the academic talk, because that's the one thing all of us like, is the academic part, the admin part, not so much. And the reason why we chose this particular topic we can discuss afterwards, so it's part of a bigger project. And I hope it's a way for us to start to just work together interdisciplinary fashion. So for instance, the topic of permutation entropy, we've done it before, we've applied it in physics, so I hope Carel will give some examples. It's been applied in financial mathematics, it's been applied even in linguistics in the past. So we think it could be a nice way to start some collaborative projects, and we have some ideas which you are welcome to stick around afterwards and discuss. And then also the whole NITheCS structure and what we are going to do and planning, and well, I haven't planned yet. You are also welcome to stick around at the end if you want to discuss any parts of that, what NITheCS is, what it's going to do, what's supposed to do, and what's going to happen in the future. So without further ado, please, Carel, take it away.
Okay. Thank you very much. Okay, so yeah, thanks. Yeah, it's nice to see a lot of familiar faces. So yeah, it gives me great pleasure. Thanks for the invitation as well. So it's kind of fitting for me to present here because this is the very building where my research in this area started. So okay, so let me just see. Okay, I will just. Okay, sorry. Okay, so the outline for the talk, I will just give a brief introduction about the background of permutation entropy. I will briefly talk about the calculation and interpretation of this sort of analysis. I will look at some results then in section 3 of research projects that I've been involved with. And basically just focus not on the specifics of the different projects, rather how permutation entropy was used to analyze the specific data sets, and then a very brief conclusion. Okay, so yeah, just to start off, I just want to acknowledge collaborators of mine who worked on projects past and present. Yeah, just thank all of them for also contributing to this, to all of these projects and to developing a deeper understanding into this. So just from historical background, so the permutation entropy is relatively young. So it was first introduced by Bant and Pompey 2002. So they introduced the permutation entropy variable H, which we will talk about a bit more going forward. So, and then Lamberti et al. In 2004 extended this analysis by introducing the statistical intensive complexity variable. We usually just call it the complexity C. And since then, so basically the sort of the big breakthrough or the claim to fame of this analysis was when it was shown that the C and H variables can be used to distinguish between chaotic processes and stochastic processes. And since then, it has been applied in many different fields. Some of them we'll be looking at in a bit more detail. Okay, so basically, at its core, permutation entropy is a pattern recognition tool. So, and basically it looks for patterns within, you could say, short-term time lengths. So how the time series varies on short range intervals. So as I mentioned, so the two statistics that is used is H and C. So C, I will just mention, is specifically used to distinguish between stochastic and chaotic processes. Most of the projects I looked at, we dealt with stochastic processes, so we mainly relied on the permutation entropy H to analyze the data. Okay, so then in terms of the underlying assumptions, so again, to emphasize, this is a time series analysis tool. So it's used for data sets that changes with time, basically. So now the permutation entropy applies to data sets that are weakly stationary. So basically, it means that the expected value at the next time step is the same as the value is at the current time step. So there are no periodicities or trends or anything like that. So if there are those elements in the data set, you first have to fit a model to remove it before you can apply this analysis. And then another sort of limitation of it is that it is not designed for data sets with repetitions. So in other words, you are mainly looking at a data set where the values are sort of continuous. So typically, like in magnetic field observations, you don't expect two consecutive measurements to be exactly the same. So it works well for that. So in other sets, like for example, in very sort of high resolution financial stock prices, you tend to get a lot of repetitions where the price just stays, it jumps by one blip or whatever, and it just stays there. So there it doesn't work quite as well. Okay, so and then as I mentioned, the method gained a lot of popularity initially, at least, because of its ability to distinguish between stochastic and chaotic processes. Okay, so some applications. So there are many more than that, but one field where it really became quite prominent is in biomedicine. So the ones marked in red are ones where I've worked in, and I will be discussing them in a bit more detail in section 3. Okay, so just very briefly want to discuss how it's calculated. And so the idea with this is hopefully to just give you an impression of what this analysis looks at. Yeah, rather than going into sort of a very technical discussion. So, okay, so just to start off, just to remind you, what do we mean by a chaotic process? So the sort of textbook example is the logistic map. Now in this figure, so the map is given by the blue equation on the top of the slide. So it's a very simple a map that if you know xn, you can find the next iteration and so on. You can generate a whole sequence of x values as long as you want. So now basically in this figure, it shows so what this figure does is basically it maps the values or the x values of the time series. It sort of projects it onto the vertical line. So for example, with r equals 3.2, so the branch has two values there. So basically it's an oscillation between those two values. So if you take all of the values from the time series after it's converged, you map it, you just get those two. So it shows a periodic, a two periodic series. So what's interesting, once you move beyond around 3.6, you can see it becomes almost a continuous set. So the series or the sequence becomes chaotic. So and the properties of chaotic dynamics is that it basically it's extremely sensitive to initial conditions. So if you take two very close, two initial conditions very close to each other over a long period of time, they completely diverge, and which makes it very difficult to actually use it for predictions, because unless you can almost perfectly calculate it, even the smallest numerical errors will cause large deviations over a long time. So now for the example that I will use for stochastic processes, so again, this is almost like a sort of textbook example, is fractional Brownian motion. So the process is sort of defined by the Hurst parameter here, denoted by HP. So when HP is equal to a half, you get just regular Brownian motion. When HP is less than a half, the increments are negatively correlated. And I will give an example of that in the next slide. If HP is greater than a half, you get positive autocorrelations, which means it's more likely to form trends. So I'm just showing here two examples. So on the left, the Hurst parameter is 0.4, which means sort of anti-correlate, negatively correlated, negative autocorrelations. So that means basically is that if you get a couple of increases, you're more likely for that trend to be broken, because it will tend more to then to cause decreases going forward, and vice versa. So as you can see there, it doesn't really move a lot, and it's quite a spiky process, the one on the left. The one on the right is where the Hurst parameter is 0.6. So there you can see it's more smooth. You're more likely to sort of get trends and so on. But both of these are entirely stochastic. So in other words, what that means is if you repeat the same experiment twice, you will get two different realizations. Right? So that's the difference for chaotic processes, that is deterministic, which means if you repeat the same experiment, you get exactly the same result. Okay, so now in this graph, so here we calculated. So this was calculated by Max and Morales. So they calculated for stochastic, for fractional Brownian motions with different Hurst parameters. So you see the green curve there, sort of in the middle of this crescent, whereas the orange dots there towards the top are the results that was obtained for the logistic map with different R parameters. Now, so the interesting thing here is that, okay, so in this curve, so you get the minimum and maximum complexity curves. So all H and C coordinates will lie between the minimum and maximum complexity curve. Now, for the stochastic processes, you find that the position on the HC curve is roughly halfway between the minimum and the maximum complexity curves. Whereas for the chaotic ones, they are very close to the maximum complexity curve. Okay. So that is how this CH plane can be used to distinguish between stochastic and chaotic processes. Okay. Okay, so let me just zoom in a bit on how the calculation is actually performed. And so it's relatively simple. So in this example, we just look at, so you basically choose a number D. So D is the number of consecutive points that you look at. So ideally you want D to be as large as possible, but unfortunately, the number of categories scales factorially, right? So it's, so unfortunately, I mean, factorial growth is much worse than exponential growth, right? So you are quite limited in how many consecutive points you can consider at a time. So in this example, if D is equal to 3, so we look at 3 different or 3 consecutive points. Now, assuming that the values do not repeat, you get 6 possibilities, sort of or 6 different ordinal patterns. So the one there, the top left, is where you just get a monotonic increase. So we call that 1, 2, 3. So the second, the one right below that, the first point is intermediate, followed by the lowest and then the largest. So that one looks, we classify it as 2, 1, 3. So, and then those are the 6 possibilities, where the last one bottom right is what we call 3 to 1, where it just decreases. Okay, so basically those are the 6 possibilities. So just as an example, so if you look at I just here generated sort of a time series on the panel on the top. So basically you look at each 3 points. So in the first 3 points, we see that it is, we call that 2, 3, 1. So we basically capture that, okay, we've got one realization of that category. So it's the 4th category there. So the next one then is 3, 1, 2. So is that one there. The next one is monotonically increasing. So it's 1, 2, 3. So we move through basically the entire time series, and we capture the number of realizations of each category. So we then calculate the probabilities of each occurring. So it's basically just the frequency divided by the total number of these subsets. So you get some probability vector. Of course, the vector adds up to 1. And then these are just the formulas. So, and this is a very sort of very fast to calculate. So the reason for that is, in the previous step, in this step, you only comparing values to each other, which is computationally cheap. And then once you've got this vector, so your probability vector P consists of d factorial entries. So all of these calculations are very fast to perform. Okay, so I'll just briefly mention. So the strengths is that, again, as I mentioned, it's fast to compute. So it deals well with outliers. So the reason for that is basically because the different categories doesn't take into account magnitudes, basically. So it doesn't matter if the next point was 10 times larger or if it's fractionally larger. It just classifies it as this one is larger than that one. And then what we've been working with quite extensively is that it recognizes, it's a good way to recognize anomalies within the time series. Okay, so the weaknesses then is that, yeah, as mentioned as well, it doesn't deal well with repeated values. So if they are repeated values, you have to come up with some strategies to deal with that. But ultimately, if there are too many of these, your results will not really be representative of the dynamics of the time series. Okay, then another important thing to note is that it, when I mention it can identify anomalies. So it basically the analysis just tells you something strange is happening, but it doesn't tell you exactly what. So you have to go back then to the data set to try to identify what is actually happening that is causing this anomaly that's picked up through this analysis. Okay, so now let me just look at a couple of results. So I will be looking at some of our papers that we published in space science. So the third one was we did an analysis of a risk analysis of the Bitcoin cryptocurrency market, and then the last one is an application to industrial monitoring of sort of factory equipment and chemical processes. So, and yeah, I'm not going to go into the details of each paper. So I just want to try to give you a sense of how this analysis was used within that specific scenario. Okay, so first one was, well, this was the very first paper. So yeah, so what I will mention, I think the point here is just that one of the difficulties with the CH analysis is that, like, for example, if if you're calculating an average, there's a very clear interpretation of the result that you get. Now, when you're calculating the C and the H, if I tell you the H is 0.9, it doesn't really tell you much about that. So in many ways, this is most efficient when you are comparing H values of one process to the H values of another process. So so in this paper, so we looked at magnetic field observations from spacecraft around 1 AU. And so we basically compared the H values for during periods of slow solar wind versus periods of fast solar wind. So this was sort of a bit surprising to me, because usually you expect when there is some driving process, so maybe a fast solar wind is caused by some activity of the sun, that may sort of cause more of a underlying driving process, which you might expect can reduce H. Okay, so so at this point, let me just mention very briefly the interpretation of H. When H is, so H lies between 0 and 1. When H is close to 1, it means basically like a Gaussian noise, which means it's completely stochastic. You can't pick up any patterns within the dynamics. So the converse of that is when H is 0, that's just either monotonically increasing or monotonically decreasing, which means it's perfectly predictable in terms of the patterns of the ordinal patterns. So basically high H means unpredictability, low H means it's more predictable. So what we saw here is that for the slow solar wind, the behavior is slightly more predictable than what you see during periods of fast solar wind. Okay, so the next paper I want to sort of briefly discuss. So this was sort of a very interesting, and it gave me a bit more insight into how this analysis can be used. So here we looked at Voyager spacecraft data of magnetic field measurements. So so here we calculated H over a very, very long period of time, and we looked at the variation of this H sort of statistic over sort of short, smaller subsets. So it's sort of like a moving average type of calculation. Okay, now what I want to show here, so in the 3 panels, on the left shows the H measurements for different bin sizes. Now, it might not be entirely clear, but what stood out was, maybe on the screen I can just illustrate this. So it might not be all that clear, but in many of so the red dashed line is sort of like a sort of upper or a lower limit for reasonable H values. Now you can see there in many cases we saw these very low H values that pops up. So almost consistently throughout. So of course it's not that many. You can see the sort of gray points on the top there. Most of the measurements gave us fairly large H values, but there were a number of these smaller ones. So what we then did was we went back to those time periods and we said, okay, how does the magnetic field observations behave during those low H periods? And what we found are examples of that. We sort of identified 6 different categories that's shown there on the right. So the right there shows the magnetic field data. And so in the first one, you can see it basically forms a sort of sinusoidal type of process, which is very unexpected for magnetic field fluctuations, which are usually very sort of stochastic and much less organized than that. So similarly, you could see there. So the one on the right, it's not as sort of nicely or as clearly sinusoidal as the previous one, but still you can see there is some sort of pattern. It definitely doesn't look like a stochastic process. So the next 2 panels shows monotonically decreasing, monotonically increasing processes, again, which is somewhat surprising. And then the bottom two shows where there's almost no measurements. It's almost flat, and just here and there, there's a sort of a spike, and then it returns to this flat background. Okay, now that might be a malfunction of the instruments or whatever. But the point I'm trying to illustrate here is that okay, firstly, the permutation entropy was managed to pick up different types of anomalies. So it's not specific to, let's say, a sinusoidal pulse or a flat pulse or monotonic increasing. So anything where it's a deviation from the regular stochastic pattern, the calculation of H is a fast way of sort of identifying these anomalies. Okay, now again, it doesn't tell us, okay, this is what happened or this is the physical mechanism. So for that, you have to go back and you have to sort of, like I said, go back to the data, look at it, and try to understand what is going on. But basically, it's sort of like like it's raising a flag. That's what I always. So I like to think of it as sort of if you what I mentioned before with the average and permutation entropy is in your car. If you have a gauge for petrol, you have a gauge for temperature, right? So petrol tells you exactly how much petrol there is. So it's very specific, but it can't diagnose anything beyond that. Right, so it's very specific, but it can only tell you one thing that goes wrong. The temperature gauge, if the temperature starts to rise, it doesn't tell you this is what's wrong with your engine. It doesn't say you're out of petrol, out of oil, whatever. It covers a wide range of things, but it just tells you, okay, something's happening here, switch off your engine, and then you have to investigate to see what's wrong in your engine. But the point is here, you have to stop. Right. So in some ways, this is similar. The H doesn't tell you exactly what's going on. It just tells you, okay, something strange is happening. Investigate further. Okay. So, and this was a very interesting sort of gave me. I think this is a very interesting application of this. It allows a quick and easy way to cover a very large data set and to look for strange behavior, basically. Okay, so the next paper, so yeah, we looked at Bitcoin prices. So this is now a completely different sort of area of research. But so, and again, I will just highlight one aspect that was very interesting to me. So in this paper, we analyzed risk, which is done through measuring volatility. So volatility, you could think of it basically as a standard deviation of the prices. So large standard deviation means large risk because there's a chance that the price can drop significantly, whereas small volatility means there are changes, but it's very small changes, so your money is relatively safe. So of course you don't want to lose a lot of money, but you want to gain a lot of money. So you have to manage the risk. So that is not too much, but also not too little. Now, so what we did here is we used gauge models basically to construct daily volatilities, and then we calculated the H values of the monthly volatility over a period of a few years. Now, similar to the previous paper, we found certain regions where, or certain months where the H would just drop down quite significantly. Now, so we went back to those periods or those specific months, and then we plotted the volatilities. Now, what was very interesting here is that we saw this pattern that emerges. Okay, and it's quite telling. So what happens at the start of the pattern, you get a large jump, and then over a very long period, it slowly and gradually sort of moves back to the original level of volatility. Now, here and there you get another spike, but you can imagine, so in these data sets, you will, so when you calculate the different categories, there will be lots of 3, 2, 1s, right? So, which means that it's just a monotonic decrease over 3 steps. which and this basically this dominance of that category leads to a low H. Now, so the picture that you get here is that sort of what happens is the initial jump is some shock or something that maybe it was a bad news report or something that happened that caused a bit of panic in the market. Now, the fact that the recovery takes that long tells you that basically there's not a lot of confidence in this market. So once something happens that scares investors, it takes very long for them before they gain back the confidence they had prior to that sort of shock. Right. So this tells a picture of a market where there's not that much confidence. Now, unfortunately for us, it's been very difficult to get our hands on financial data. Usually people use it to make money, so they charge also a lot of money for the data. But I think it would be very interesting to do similar studies to see how other markets behave and whether this sort of period of recovery can be used as a way to determine market confidence, for example. Right? So how quickly after a shock was introduced does it recover? And again, so this is sort of the interpretation. Now, permutation entropy doesn't tell you this picture. It just warns you something is happening here. And it says, now it's up to you to find out what is happening. So this is not a pattern that we were looking for. We basically, because of our permutation entropy analysis, we managed to identify this. So I thought that was very interesting. Okay, and then finally, okay, so this is again another application, which is basically where, so it's sort of monitoring instruments. So it's kind of related to that Voyager data that we looked at. So here we are looking at a chemical process called the Tennessee Eastern process. So now there's been simulations done on this process. So basically, what the simulation does is it look at a whole bunch of different outputs from so some of it is like temperature measurements, some of it is like the output of the whatever is produced by the process and so on. And then it simulates what happens when different faults are introduced into the system. So what we tried to do is we wanted to say, okay, can we now, in a similar way that we saw those drops in H, can we use that to identify when a fault has been introduced into the system? Okay, so now in an earlier paper, we managed to show that there's definitely a difference between the normal operating, so H under normal conditions versus H after a fault has been introduced. Now, basically what we wanted to do here, so we said, okay, so you can use it to identify, but now we want to use it to sort of, to be able to quickly pick up. So soon after the fault has been introduced, as quickly as possible, we want to be able to identify, okay, there is a fault, so we need to maybe stop the process, we need to fix this before we continue to avoid damage and so on. Okay, so what we did was we compared the permutation entropy to another sort of industry standard method, which is called the cumulative sum, or Q-sum for short. Okay, so the results. Now, basically, we sort of identified two cases. Now, in some cases, okay, so there's a lot of figures shown here. So on the blue and orange panels on the left shows cumulative distribution functions. But for now, let's just look at the raw data on the right, those purple curves. So for the two on the left there, you can see that, so it's maybe not that clear, but there's a green dashed line where the fault is introduced. Right. So for the first two ones, we see that immediately the value increases significantly. Now for these types of faults, we found that the cumulative sum can basically pick up the fault faster than our permutation entropy analysis could. Okay, so that is basically represented by, okay, let me just go back to this. These panels shown over there. So the basically it's a cumulative distribution function. Now, in essence, the steeper it is, the better. So for these ones, the orange curves they shows that cumulative sum picks it up faster, and it sort of makes sense because cumulative sum basically looks for values that are beyond the, let's say, the 99% confidence interval of that. So it will pick it up very fast, whereas permutation entropy requires some time because it has to look at the previous 30 entries. So it takes a while before all of the entries in that subset of 30 is covered by the sort of by this increasing pattern. So for these types of faults, it's better to use the cumulative sum. However, we found certain faults like the one shown there on the right. Again, let me just use the mouse to show this. So now over there is where the fault is introduced. And here we see that it takes a little bit of time before the sort of wild fluctuations kick in. And for these types of faults, we actually found that the permutation entropy, as shown in these two graphs, permutation entropy was actually able to pick it up faster than the cumulative sum. So, and basically, so what the reason for that is after the fault is introduced, the behavior becomes more regular, but not in terms of the magnitude. So for the first faults, for these ones, it's better to sort of monitor the magnitudes of fluctuations or the magnitude of the value itself. These ones, it turns out that it's better to look at the sort of ordinal patterns, and it allows you to pick up the introduction of this fault faster than you could. And again, I think for instrumentation, monitoring, and that type of thing, this could be very, very useful. Okay, so in conclusion, so basically the way, I think there are different ways that you can use permutation entropy, but what we found is that for in order to identify this anomalous behavior, it's a very, very useful tool. So as mentioned, we just mostly use the H of the sort of CH combination to achieve this. And yeah, we were able to identify unusual behavior like those patterns you see in the Bitcoin risk profiles, and also some very unusual behavior or malfunctions. And yeah, so I do believe that this is still relatively young or relatively new sort of tool for data analysis and time series analysis. I think there is a lot of scope. Then in the end, I wrote there a quote that nobody has ever said. So, okay, so that concludes it from me. Thank you very much.
Okay, thank you very much, Carel. So I think we can start maybe just with questions about the presentation itself. Specific questions. I need to check the Zoom as well. Okay, so you have time now for questions officially. Comments, criticism. I have one question about the Bitcoin.
Okay.
The time it takes for the volatility to decrease, is that always the same?
So you're basically looking at 30 entries, right? So if it's only 5 entries, it might happen, but you might not pick it up with this age. So the ones that we could identify were ones where it would probably take at least, let's say, 20 days before it settled in. So yeah, but as I mentioned, I think that duration of recovery could be a very interesting sort of measure of how big was the shock and how much confidence is there in that particular market. So, yeah.
Just the length of the news cycle. Okay,
Maybe.
There's no more questions. I'm going to. There's a question. So what about?
Okay. Okay, so the thing with C, okay, so you so basically what typically your first step is you're working with a data set. So you can take the entire data set, you calculate H, you calculate C, and you can conclude, okay, it's a stochastic process. Okay, and so then what, right? so basically, so what that means is that. Okay, but that's actually a very good question. So you could think of it roughly like as at different times, you will typically see if you monitor the CH plane, right? The movements will be sort of roughly speaking along this curve, right? So because it is stochastic, the C will sort of follow the values of the minimum and maximum related to the H value, right? So basically, so if where it would be useful to calculate C as well is if you suspect there might be a region or a period where there might be a transition between a stochastic and a chaotic process, right? So then monitoring the both the C and H will be useful to identify maybe a period where it transitions from one type to the other. But so basically, our underlying assumption was, okay, we are dealing with a stochastic process. So in other words, we don't care that much where it is on the C scope. We only want to determine that sort of predictability of the stochastic process. So I hope that makes sense.
Yeah, and then I see Renee, you have your hand raised.
No, it's not Rene, disappointment, it's me. No, thank you very much. I wanted just to thank Dutoit and the speaker for organizing this very historical webinar, and I hope there will be many more like this in the future. So thank you very much. Sorry, I was trying to raise funds for NITheCS when the webinar started. I only started listening halfway through. Thank you very much. Thank you for the nice talk.
Thank you very much, Francisco. So I think that's all we have. Oh, there's one question.
Does the level of stochasticity or chaoticism matter in determining how? So if you have two processes that differ in the level of stochasticity or how chaotic they are, does it matter if those are fairly close to one another, but there is still a difference between the two, or to what degree does that matter?
Yeah. Okay. So yeah, it's I would say it's a little bit loosely defined, right? So so in terms of chaotic, usually as long as it's close to the maximum complexity. So, and I think those orange dots shown there gives a good indication that for different processes, it covers quite a wide region. Some of them are very, very close to the maximum. Some of them are a little bit down. But basically, it's I would say sort of like a ballpark estimate that you make. So you would say as long as it's relatively close there, and ultimately, and I do think that's why these two processes are sort of good to, because as I mentioned, it's good to compare different. So it's difficult to interpret the numbers by themselves, right? So you can now say, okay, so if you get something relatively close to the maximum, you can say, okay, how does this compare to the logistic map or to a Lorentz attractor or some other chaotic processes? So that would be sort of my advice on how to, how to cover that. And then likewise, the fractional Brownian motion gives you quite a wide range of stochastic range in H for stochastic processes. So I would say sort of compare and then see how close it is to the different ones. So yeah, but it's not a very exact science, I would say, at this stage.
Thank you, Carel. So I think I can close the big brother. So sorry, Francesco, the race is confidential.